Okay, another quick check with this ray coding. Let's see if it is the computer. Let's put it fully on. And yeah, let's go.
Is the slider next to the bar?
This one?
No, that's the thanks a second. Outside the
Yeah, you should let me slide, but it's not.
Oh.
You speak. Here, speak loudly. Say hello.
Hello.
The green didn't change. Okay.
It's beeping.
Yes, it's just beeping. Can you pick up, I'm sure, the amplitude in the statistical manner? Okay. We don't know what we will get, but let's keep going. Is that okay? Yeah. So, it is lecture. Wow, we've made a lot of progress. And I will start with the slide. Let's see. Time-dependent quantum mechanics. Still built on time-dependent Schrödinger equation. Yeah. So we're going to use that. And we will wrap up chapter 3 of our book. It's based on what could be described as the 5 postulates of quantum mechanics. Those postulates were given in the chapter one after the other. And we have shown some of them, for example, when we said boldly. Here is the postulate that to every observable there is a linear operator, yeah, which we call a Hermitian operator, that when put before maybe the state vector, it gives us eigenvalues. When operated on the state vector or the state function, it gives us eigenvalues. That's the postulate. So we've done up to 5 of them. And the last of them is this: that the state of the system represented by the state vector evolves with time between measurements. And that if you then have measurements, like trying to measure the position, trying to measure the momentum, the state vector collapses into one of the eigenstates of the operator representing the measurement. These are very carefully put words. So the state vector, this is the general one. If you measure momentum, this state vector collapses into one of the eigenstates or eigenfunctions of the momentum vector that is measured. In other words, measurement does something to your quantum mechanical state. And it can be confusing taking that into the macroscopic level. It leads to paradoxes. What was the state of the cat before the measurement? It was a linear superposition of what is possible. Take that to macroscopic level, cat alive or dead or sleeping. Cat alive or sleeping. Take that macroscopically, the paradoxes become almost unacceptable. Like you are not speaking, you are not making sense. And the paradox actually comes from Schrödinger. And he used the system here with cyanide being released when a microscopic event happens, Geiger counter. So there is radioactive decay, which is statistical. If one radioactive nucleus decays, then it should trigger the Geiger. The Geiger counter should record, then it should trigger some circuitry to release the cyanide. And then the cat might be dead. We try to use that to represent the paradox of what measurement means in quantum mechanics. And And that's where you can now begin to read your afterwards. But we are going to focus on what we can calculate. Based on all we've dealt before, the statistical interpretation, and see that at the microscopic level, microscopic quantum mechanical level, this works. When you try to extrapolate it to our macroscopic level, you will be successful as long as you apply Ehrenfeld's theorem, that at very large quantum numbers, we get the same result as classical physics. And what does that mean? There is progress in this understanding this paradigm. Some people now talk about decoherence. That at the macroscopic level, we are complicated superpositions of so many possibilities, the multiverse, not the universe, and all that. It gets more interesting. It gets closer to philosophy. It goes a little bit away from physics as we know it to go up. Maybe philosophy or something like that. But the basic physics works. As systems we know exhibit quantum mechanical properties. Let's focus on that for today. Is that okay? And illustrate some of these with calculations. Okay. So the 5 postulates, then we will make use of the operator method to go through those 5 postulates. And our scheme is to make sure that everyone is happy with quiz 7, knowing that you're going to continue reviewing linear algebra in the appendix. So, one part of it is that you soon use what you reviewed nicely. You're going to calculate Hermitian operators as matrices. You're going to find out that the Hermitian operators are actually symmetric matrices. And you're going to see that when we say it is Hermitian, it has 2 main properties, namely self-adjoint that has 2 aspects, 2 properties. 1, transpose. 2, complex conjugate. So when we say it is Hermitian, we mean you take the transpose conjugate. Make a transpose of your matrix. Make a complex conjugate of it. And if you get the same result in applying the matrix, I can see people who are nodding because they read it. And then we'll have explicit examples. So today we wrap up with the Dirac notation applied to time-dependent Schrodinger equation. And then the next class is explicit matrix elements calculated, proving that something is self-adjoint, big transpose, and things like that. So to prepare you for the next homework in which you will actually calculate eigenvalues using linear algebra. Alright. So you know, and you've seen this picture before, this is where they worked on some of these systems, and it's only repeating it here. So quick summary of systems we have studied. Systems where measurements lead to collapse of the state function to one of the eigenfunctions of the operator you are using, of the measurement you are using. Systems where quantum mechanics shows up nice. Look, we did the step potential. Look at it there. Which physical system? Conduction, electron near surface of matter. Yeah? Look at that. Step potential, energy above stop, neutron trying to escape nucleus. Barrier potential, something we did. Alpha particles trying to escape Coulomb barrier. Oh, there are many more. And so you can look at the probability density, which is the statistical interpretation side side side. And see what it gives you over the other side. See it internally. Yeah. So, let's keep going. More systems. We did barrier potential in which the energy is up there. So scattering state. That's what Griffith called it. No reflection of certain energies, and we calculated that we showed graphically in my slide. Finite square well potential. Look, we have some bound states, and typical system is the neutron bound in the nucleus. Yeah? It stays there, locked there, but especially for nuclei that are stable. So we have it there. A little bit of possibility of finding usually stays in there. Then find infinite square well potential molecules strictly confined to a box, so an artificial stuff. And we've seen that in what? Quantum dot. Yeah, I will be pleased with it. Alright, so simple harmonic oscillator, same thing. These are quantum systems we're talking about. When measurements can use to collapse the wave function. We can verify the Schrödinger equation, the Copernican interpretation, or the statistical interpretation. So here are the 5 postulates. I can write on the screen some of the ways in which we presented that before we move on to the board to show the application of the postulate 5. That's our aim for today. We will revise the postulate to make more sense out of it, and then focus on applying postulate 5, which is time dependent. So far, any questions? Alright. So the most complete knowledge of a system is represented by a state vector. What else did we call it? Anybody? Wave function, but make it more, yes? Eigenfunction. Yes. So eigenfunction. State function. Okay, so just recall that. We are using chi just to make it as general as possible. We can still represent it as we had before. So, as a case, state case. In that case, we are representing it as this vector. So notice that with the Dirac notation, that's a vector. In which space? In which space? We are revising.
Hilbert.
Sorry?
Hilbert.
Hilbert space. State vector is Hilbert space. And what is Hilbert space? What is Hilbert space? Okay, so let me make the kind of revision there for number 5. Number 1, so one of the postulates. So we got our chi. We recall that we presented it as phi, and we are saying that it is a state vector in Hilbert space. And what is Hilbert space? This happens in Hilbert space. For instance, what does this mean? So, in Hilbert space, we can get this. We can normalize, we can get the statistical interpretation to work because it is the space of square integrable functions. Those vectors allow us to get that function forward the best space. So, back then to our slide. For every observable A, there exists a linear emission operator, A hat. The result of the measurement of A must be one of the eigenvalues AI of A. So what does that mean? We can go back to the quote here. Number 2 means, yeah, A hat onto this should give what? Anybody from what we said in the previous? Yeah, right there. AI what? Complete it? Anybody? Class. Yeah. And for this to be true, it means that psi itself is one of the eigenstates that is possible. I'm sure that people have produced a lot on that, but that's good. That's a lot of words, but that's what we've been doing, okay? Can we do number 3 then? If the eigenvalue AI corresponds to eigenstate psi I, then the probability of obtaining the result AI where the system is not state is psi chi. Yeah, that's nice. It means that we have a way of making psi to pick out its corresponding components in the main D state chi. Yeah, we can pick out its components and allow us to have psi star psi. Yeah, it could just mean something like this. Here is the vector chi, and we can take proper basis. We want to get position out of chi, so we can get the base. We can get the component of chi that gives us position. And to do that, it means that we end up with, so this component is that, which allows us to get the position along here. It's an abstract vector out there, so we can get components that are eigenstates of the operator we want to use. In this case, and the square integrability means then what we just saw there. Okay? All right, let's revise number 4. As a result of the measurement A in which the value of AI is obtained, the state of the system is changed to corresponding eigenstate. Yeah? Of the state. So measurement does something fundamental to our system. State of the system collapses to one of the eigenfunctions. So eigenstate corresponding to the operator that we are using, corresponding to the measurement. And so lastly, our number 5. Between measurements, then what happens? Happens between measurements. The system evolves, yeah, with time in this abstract vector space. And we can apply the Schrodinger equation on this abstract vector space or even on any of the eigenstates equation. Any questions so far? Okay, let's see where we are then. I'm going to let you read that. I wouldn't spend much time on it. Okay? But our big thing is the postulate leading to number 5. So we're now going to apply number 5, the time evolution of the space vector. So, let's do that. Please play. What number are we in terms of writing out stuff?
I think it should be 26.
26. Sure. Can anybody confirm? 26 was not 25. I thought it was 27, maybe?
26.
26. Oh, thank you. So, class on 26. What should we call it? We're going to prove. We're going to use Dirac notation, use operator method, use time-dependent Schrodinger equation, yeah, to apply some of what we already know, but as a way of illustrating this whole thing about time-dependent quantum mechanics. So let's apply it to a nice proof that we've already done. Proof. Okay, let it be like a problem. Proof that one normalized So we're going to do that on the state vector. The state vector remains normalized. Okay? State vector remain normalized. So that's the problem. Why have I chosen the problem? It will allow us to use time-dependent Schrodinger equation. So what that means is, let's say, statement of the problem I will show that I'm going to write it for you. Psi, the Dirac and K prime derivative of it equals what?
0.
0. So we want to show. And it will enable us to use the time-dependent Schrodinger equation. So without much ado, let's write down the time-dependent Schrodinger equation which we are going to use. So what is the time-dependent Schrodinger equation? Yeah. I hit bar. I shall this equals what? That's good. So let's write it in a different way that we are going to use over there. Let's make it a full page to still work. And say VDC equals then 1 over what? I H bar, yeah, H. And the Hamiltonian operator. Are we happy with that?
Wait, how do we make it a full derivative?
Yeah, because we can, it will work even if we make it partial.
Okay.
Because psi is x comma to psi of x comma to. It's only a few, it's only a
Okay.
it will work with partial derivatives. Okay. So, we are going to do the next one. I just did it on the, let me write it even more interestingly, which also illustrates something. It will be the same as 1 over I H bar Hamiltonian operator. Sorry, the very thing I want to remove. So Hamiltonian operator psi. So we've got this big, nice text. I say text. So do me a favor, please, and get me the other one with the Dirac. Yeah? Can we get, because we need both with this product here. So we'll need VDC of that. Yeah? What I mean is can you do that for me, please? What might it be? Everybody? Or anybody can just step out and show. Hey, you can show on the screen. Yes. I'm just trying to relax a little bit.
Yeah.
Thank you, Carter. Keep going, yes. Yes, that's it. Very good. Thank you. Anyone agrees? Yeah? So we got that. And see where we need it shortly. So we'll be getting back here. Let's then apply the product rule here, okay? Which is true? Yes.
Would we need a negative for y in the denominator?
Not yet.
Not yet.
Not yet. Good one. And that's part of what I'm illustrating, because you need to understand this with Dirac notation, and then we'll see it clearly in the matrices themselves. So, let's do the product rule, step 3. Apply the product rule to what we had. So we had these V. What will that be? Equal to? Yeah? We can, since people were like, let's do partial, okay? We can do anything we want. So, partial C of our psi is psi. So let's put it right in there. Look. Here, keeping this one constant, plus, what should be the next one? Yeah? Partial C. Are we happy? Alright. So let's just fit in what we saw previously. What was partial psi, partial C? Yeah? The same as this one. We got it already? Call it partial psi, partial C. It works. See what it is right there. Is that the one we got first? Yeah, this one. We got this one.
Can you move the time derivative inside?
Yes.
Okay. I just wasn't sure.
Just do something to it. Yeah?
Yeah.
So let's take this over there. Take it over there. What was it, please? 1 over I h bar. Are we together with h? The Hamiltonian and psi. So that was the graph. What else? Plus? Okay, so we need a psi right there. We just took this. Put it in there, put back our psi in the kit. And then we put our graph psi over here. And what will be our partial psi, partial C? We'll do that. We'll take it from what we did before. Yeah? 1 over I h bar h. So 1 over I h bar. Yeah. That is good. Here is the small magic that I wanted everybody to see. Cut it off there and remind you psi star equals that. You agree? And if you do, it means that everything inside this bra is a complex conjugate compared to this. Is that okay? Complex conjugate of I h bar is what? That's where the negative comes from. So, negative 1 over I h bar. And then we can continue with our h psi in this bra, and then put our cap, and we can also pull this one out if we want, okay? If we pull it out, will it be a negative sign? Great. It will not, because it is coming out of what? A cap. Yes. So, 1 over I h bar, yeah? Any questions? So, what else can we do so that we prove that this whole thing is real? We just got a negative.
Anything else that the Hamiltonian operator is missing?
Correct. Yes, absolutely. So maybe we can call this step after you, Joe.
Joey step. The Joey mission.
Okay, so the Joey step is to know that this Hamiltonian is Hermitian. Wow, we are talking real language here. The Hamiltonian is Hermitian. And we know exactly what it means, right? Let's make that explicit. Let's make the Joey step very explicit and say, okay, this is negative 1 over I h bar. So we're going to send our Hamiltonian over from the bra to operate on the X, and it is going to pick up its hermiticity, right? So we put our bra and send our Hamiltonian there. And what happens to the Hamiltonian operator with that? What happens to it?
It's just itself. I mean, it would give.
Yeah, I agree. Let me not waste your time since you know what we're trying to do. Yeah. It will eventually be itself because it is emission, right? So, plus, yeah, 1 over I h bar psi Hamiltonian. Yep. So what can we then claim? We can claim immediately, without further ado, 1 over I h bar psi h psi plus 1 over I h bar psi, and give the reason right away. That h will give the reason somewhere by the side. That is the jury step. Do we agree? Any questions? Okay. And this then equals 0. I thought it was still easy. So this allowed us to use the time-dependent Schrodinger equation to play with Ketz and Brar and some calculations and what operators do, emission operators, and things like that. That was the answer. So we're now going to do some exercises after 1 or 2 minutes break. How many minutes do you want? 1 or 2?
2.
2 minutes break, and we'll do some exercises. All right, welcome back. It is time to continue time-dependent quantum mechanics and Dirac notation. So let's get back to our slide. What we just finished, so that you see it's right there on the slide for you. Done that. Okay, so let's then try the next problem. The next problem is over here. Let's get class exercise. Yay. Any part that is not visible is visible here. So work together. That's good. So you now measure, yeah, what will happen. What does measurement do? The test of our understanding of postulate 4. So, do your group, please. Where are the groups? Is it a group? Good.
Yeah. Because it has to collapse into you have to choose one that like it would become either 1 or 2.
I feel like
What do you choose? Go ahead. It's not right because you have to choose one of the bunch of negative equals that
I know.
Oh, okay. So A and B are wrong.
D is a superposition of both of them.
So I'm waiting for the group that has arrived at something. Is this one group?
That means the delta function is not. What is a delta function? It does. It goes after the measurement. It goes back to something else after. I promise. Or we just said it. You literally just said it. Yeah, you're like, oh, we have to that.
I would not believe you if I didn't remember it.
It's C or E. Because, like, actually, the cat doesn't do it. The cat's always yeah, no, I remember. I have C or E, I think.
Yeah.
I don't know what a delta function is.
The question wishes you to really grasp the effect of measurement. It's about the effect of measurement. What does measurement do to the system? Something that is very non-intuitive. When we say the state vector collapses, what do we mean?
Is that what a delta function is? Well, that might be also Jared's wrong. Jared's definitely wrong.
Delta function has zero. The delta function is at zero. The delta function has non-zero value only at zero. So that's
then we'd like to confirm our answer.
okay.
At C.
Okay.
We choose C. Yeah. We're gonna Dr. We're gonna vote for B. Yeah, we have B. C.
Good, good, good. And they have C. C. I said it's non-intuitive. Your eye is actually very good, but you're adding something to postulate 4 that you don't need to add.
So we're all wrong.
That's the meaning of collapsing.
Oh, okay, yeah. It remains in the energy eigenf future.
That is the energy eigenstate. And that energy eigenstate itself can evolve, but it is now that energy eigenstate.
What does it mean it evolves if it stays the same?
So as an eigenstate,
Yes.
yeah, it contains all information you need at any time, any later time. So that is now an eigenstate, no longer the original state vector. Now an eigenstate of what it has collapsed, and it is evolving according to that eigenstate.
Okay,
Not the original.
So with the cat, that would be like,
Please. Okay. I'm not going. I don't want to go there. I will not succeed.
So it's saying that once you measure
The cat thing, the paradox is to show the paradox. Yes. Exactly. You got it.
Oh, it's a different size.
Yes. You said it nice. It's almost like having a different size.
Okay.
But that size one that was already contained in the state vector in Hilbert space. Yeah.
If you measured it again, would you get a new eigenstate that only could be inside of that, or?
If you measure it again, and it's a careful measurement, like our book says nicely, you should get roughly like the same result.
Okay.
Yeah. Yes. Yes, that does it. Good job. So at least the thinking was good. Yes. And you chose choices, you made options that are really good, and were really good. Good. So let's do this one.
Actually, wait, we haven't measured it, so it can't be eigenstate yet. Then it's gotta be, I actually really like that. Why is it not the negative?
Yeah.
Like you see how the decaying line.
And also in our solution on board. So which group is sure?
We're not talking about it, not at all.
They look so similar. Yeah. Why do you think it's B?
I don't know. I don't think it's C because that requires that someone.
Right. So someone has, let me make it easier, correctly eliminated E2. Yeah? Why must it be E2? So look, at time t0, the wave function for a particle in an infinite square well of that is this, where A is a suitable function. Which of the following statements is correct about the wave function at a later time? It collapses to one of them, yeah, one of the eigenstates, which will be a linear combination. And how do we pick up those linear combinations? Those expansion coefficients that are proportional to the state that it collapses in. If it collapses into E2, then C2. If it collapses into E3, then C3. Collapses into E4 plus E5 in a certain linear combination, then we want C3, C4 plus C5 in that combination. Does that make sense? So we have a way of fitting whatever it will collapse into. So pick your choice there. So those for A, those for B, those for C, those for D. Excellent job. This is D. Yes.
What is that?
Go for it.
We don't have the original wave function there.
Exactly, that's the idea. You don't have the explicit form, but you have the solution, the general solution. You've got the general solution. Therefore, you've got a general expression for whatever it will collapse into. And this expression picks up all the things in that solution, the quantization, the end. Remember, this is the general solution, which you will find out to be quantized if you want to normalize. Yeah? It has to be quantized. It is an infinite square well. Yeah? So that's the way to express a full solution with it equal to n. The Cn taking the place of A and normalize. Yeah? And the n itself taking care of the quantization. And this taking care of the wiggle factor. The energy dependence is all up there. So that the square integration will still give you normalization. Even this is normalized. Normalize this, it will stay normalized. Because this goes away inside side. And leaves it with this. It's normalized. Yeah? Find that Cn squared itself is still 1. Yep. That's it. And you did a good job getting that far. Let's do this one. Now apply it to a special case in which the Carter said we didn't know. Now you know that originally it is just a linear superposition of 1 and 2, psi 1 and 2. Now get it. That one was the general way to express it. Now let's show it with just 2, starting out with a linear superposition of 2 states. Just before.
Either A or C. C is like the general solution.
So speak maybe just a few things to convince yourself, then we choose. We make our choice.
No. Actually, yeah, because if T is equal to 0, then I can't. Go away.
Okay.
I don't know. T is equal to 0.
Then it's equal to 0.
Yeah, it's 1. So then because of everything you had before. Isn't that what we're supposed to have? Yes. So A?
They're both right.
No.
No.
A is only right.
It's 0.
No, wait. A is only right for T.
But it's at complete.
No, it doesn't. It's actually for a partial extent. Oh, so it does have.
Just before T equals 0. So T equals negative time, right? We're in quantum mechanics. Just before that. It's a way of making you see what we mean by this linear superposition and tagging on time dependence until something happens. Yeah. So the full wave function with its time dependence is what you want to express before you even measure. Are you sure? Okay, it is quantum mechanics with reasonable probability. Yes. So let's give it to Joy. He was very bold about it. Yes. Actually, I overheard his reasoning before arriving at it. And he actually corrected something. Yeah, but the time is still there. Cool. So I was impressed. So good job. The time dependence is still there. put whatever time dependence it is, and you get back what it was. Yeah? This was at t equals 0. That's why it kicks out that thing. At t equals 0, you get this state vector, yeah, which then kicks out the wiggly time. Hey, if this is not t equals 0, but something else, how do you write this? That's wrong. And then it played a lot of tricks on you. Okay, let's see where we are. Should we try one more, or should we go into more lectures on the slide?
Let's do another one.
Okay, like that. One more. Okay. And this is like a repeat, just to kind of see whether we still retain what we've learned. The range is already given, so the integral, the integration is expressed in this in the region between, so we've already spoken integral there. Make your point true. Looking through. Just to make sure we're not forgetting definitions. So, and don't let the Dirac notation confuse. Okay. So, at t equals the initial state of the particle in the infinite square world is that. You measure the energy of the particle at time t equals c naught and obtain E1. So the system has collapsed to. Then you immediately measure the position of the particle at t equals c naught. What is the probability of finding the particle in the region between that? So, remember, state vector, chi, very abstract. Then, you measure and get an eigenvalue AI of the operator A. The system is now in one of the states, the eigenstates of the operator A. In this case, the operator is position. How do you express it? Yeah? Something times the original vector or dot inner product. Yeah? Vector. Just notation. So make your choices again. And there's not one way of writing it.
Yeah, I agree.
So we showed how to write it in two ways, right? So that's just what we are checking. We could write it in the old way, yeah, and then we could write it in Dirac notation. In both cases, we get our square. Any group happy with the out result? Any group wants to share? Yeah, you have some idea about it. Okay, so can I repeat the hints I just gave? Let me repeat the hints. So let me repeat the hints. So there are two ways of writing the same thing. Yeah? Two ways of saying. Okay. Now that the system has collapsed into this state, here is how we write it in Dirac notation. But it's still going to be the same thing as our old notation. Is that okay? So take what it should be in our old notation, tag on the Dirac, and you should arrive at it.
Like, so we can do right, but like psi 1.
All right, let us vote. Those for A, those for B, those for C, those for D. Most of you are D. None of you enjoy your good work. Excellent. So, great. Just keep inside the notation as we go along. Can you see the new thing?
Would you write that out in an integral so we can see what that looks like?
Exactly. I can make you write that out, so you write it out.
I'm actually asking how you write it out.
Yeah, because we've done it before. I'm like...
Well, I know if you have psi and psi, then it makes sense, but I don't really, like, I don't know how you take an inner product with x naught. Is that also... Like,
no, this is like a vector now. This is like an operator now.
okay.
Remember when we said it collapses into psi I from chi, and we put the psi here and the chi there. Yeah. That is how we get it. I'll get back to that slide for you. But this is simply the same thing as okay. So we're saying that it will just give us that's the x naught psi here with x here. Since the integral is spoken of in the problem, we can write it as, or let's relate to the based on the problem here. So, like, it will still be whatever x we got there, here, x, y. So we can be more explicit and say it is the x that we got from this process. And I can show you the time. So this is the same as what we have here. This one.
Is x not like the wave function at x not? Like basically like the...
Exactly.
Okay.
Yes.
The notation
So,
is confusing.
right. So now we say it collapsed and obtain E1. Good point. We got, I like your question. Like, and you ask them at the right time. So because we got E1, what is now psi? What is the index for psi now?
Psi 1.
Right. So that means that we got psi 1. And now I was trying to write on this. This is the psi 1 and whatever it was. So I put I there for whatever the measurement was. Is that okay? Yeah. So we can be explicit and say 1. Because in this case, that is what it was. Okay? So in general, it is whatever you get out of this. So for example, if you had measured and you got psi 3, what will it be there? That's why I kept it general. Yep. This collapsed the system. So psi 3 was the eigen, complete it for me, the eigenstate of the operator x naught on the state vector psi.
Oh.
Yay, clicking.
Yeah, that makes sense.
That makes sense. I like that. Yes.
So for is one just the probability of finding the particle at
Sorry?
X naught? One on the that's just the probability of finding the particle at X naught. The option one in the yeah.
Yes.
Okay.
That's the probability density. But we've now written it out as an integral. And to do that, you have to specify the region. It's about accurate truth. People are getting it. I'm happy too. All right. Okay. So let's get back. This question contains a lot, right? Like if you don't look, psi looks like psi 1.